very good morning, respected resource person for today's session, Dr. Kailasnath Madanan, and dear participants. I welcome you all for the last day of this Atal Academy sponsored faculty development program on photonics organized by Department of Physics and Electronics, Rajarshi Shahu Mahavidyalaya, Latur. At the outset, I would like to welcome Professor Kailasnath sir for this FDP. And I request one of my colleagues, Mr. Vijay Jadki, to introduce today's guest. Mr. Vijay, please.
Good morning, all of you. This is the 13th session of our FDP program. I am Vijay Jadke, welcomes all the participants, and today's resource person, a very great personality named Mr. M. Kailasnath sir. Mr. M. Kailasnath sir currently working as professor at International School of Photonics, Cochin University of Science and Technology, Kochi, Kerala, India. Respected sir completed his MTech in optoelectronics and laser from Cochin University and received PhD in photonics. Professor M. Kailasnath sir completed his postdoctoral program in biophotonics from Texas University, USA, which is really great. Respected sir is doing supervision for more than 5 research scholars. Professor M. Kailasnath sir is very much active in the photonics and optical fiber research areas. Thank you. Once again, I heartily welcome Professor Dr. M. Kailasnath on the behalf of Chief Coordinator of this beautiful program, Dr. Abhijit Yadav sir, and Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur, Maharashtra, India. Thank you, sir.
Thank you, sir. Please, sir.
Thank you for the introduction. So,
your PPT is not visible now, sir.
Not visible?
You click on PPT.
Is it now visible?
No, sir.
No.
Now, yes, now it is.
Is it visible?
Yes, sir.
Okay, now I can start?
Yes,
Is
sir.
it
Yes,
coming?
sir. Please.
Okay.
Yeah,
Okay.
but it is not on slideshow mode.
Just a moment.
Yes.
I will just once again maybe.
Yes, it's coming, sir. Now screen is shared, but a web page is seen, sir. Yes, now you click on PPT, sir. Your screen is visible, but PPT is not visible. Just you click on the PowerPoint, yes, sir. And then open your, just you put it on the slideshow mode, that's all, sir. Yes, sir, fine, sir.
Okay, okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay.
Yes.
Thank you, Dr. Abhijit, for giving me this opportunity. And thank you for the nice introduction given. I once again thank the organizers, Rajarshi Sahu Mahavidyalaya Latur, and I think they are inviting me for the second time. Last year also I was here for a talk on a similar topic. Very good morning to all the participants. Today I would like to discuss some of the research that we do at International School of Photonics, Cochin University, with regard to some micro lasers. So we are all familiar with huge laser systems which are used for many research and development activities. But I'm going to tell you the lasers with micrometer size, which can be very useful for sensing applications. And this has to do a lot with the human effort from ancient days to trap light in in certain locations. It is said that from ancient days, human beings try to trap light in bags, buckets, and cans, etc., even though unsuccessful. But in modern optics and modern science, that purpose is actually served by optical microcavities, and they try to contain or confine the light for a relatively longer period of time. And of course, an ideal optical cavity of micrometer size must confine light forever. That means without any losses. But practically, the confinement time is very much finite, and it is described by a factor called the Q factor. Okay, so in any conventional lasers, we have a two mirror cavity and a gain medium in between, and that gain medium is pumped, and then it actually generates light, and the efficient recirculation of the light in between the two mirrors actually leads to constructive interferences, and then in that way it is also actually trapping light for some time. But that kind of confinement, it is not very easy because it is limited by the reflection or the reflectivities of the mirrors used, its alignment, perfect alignment of the mirrors, and the size of the cavity, etc. But if you think about a laser which can act as a very efficient sensor or a resonator without making use of any mirrors, so that kind of concept is based on, is acting on the micro lasers. Like you don't have any mirrors, still it is acting as a laser. It can efficiently keep the light circulating within it. So that is the idea behind micro lasers. But before going to that, I will just give a brief introduction to my department, and also about some basic concepts about the sensing using light, and what are the type of sensors that we generally use, basically which are working on the principle of fiber optic sensors, or surface plasmon resonance sensors, optical fiber Bragg gratings, and those kind of things I will just go through in quickly before entering into the micro lasers. So first of all, I will move to my department. My department, International School of Photonics, established in 1995. It is a center for research and higher education in light-based technologies, and it was recognized as a center of excellence by the University Grants Commission. And based on that, we started a 5-year program on MSc Photonics, which is the unique program, one of a kind in the country. And we started it in 2001, and it is successfully generating manpower in the field of optics and laser technology and fiber optics and all. And most of our students or graduates, they find opportunities in, in foreign countries, as the photonics related R&D and companies are actually emerging in India, but they are not well established compared to the situation in foreign countries. So the qualification or the eligibility for this 5-year integrated MSc is a +2 with a good score in common admission test conducted by the university, Cochin University. And we also conduct, and the intake is 20 students are admitted every year. So at a particular point of time, you will have 100 students in 5 batches. It's a 10-semester program, and during the 10th semester, the students usually go for a project, 6-month project, and many of them get opportunity to do their project abroad at reputed institutions and R&D centers, universities across the globe. And we have another program, which is a 2-year MTech program, Master of Technology. The eligibility for that is either a Master of Physics, Master's degree in Physics Electronics, or it can be a BTech or BE degree in Electronics, Electrical and related area with a valid GATE score in the concerned branch of study. So that is the qualification, and again the intake is 18. So around 38 students are totally admitted every year in under MSc program and the MTech program. And we do have many MOUs signed between many universities and institutions, and we have these MOUs working actively for student and faculty exchange, and most of our students get opportunity to work with these universities abroad. And I'm happy to say that 6 of our MTech students of this batch, they left for the University of Gothenburg, Sweden, 2 days ago, and they will be pursuing their 1-year master's project at Sweden in University of Gothenburg Department of Physics. And the faculty, in a glance, we have now we are 9 actually. One more faculty has joined. We have laser plasma related research, then optical fiber sensors, then non-destructive testing, laser spectral metrology, chalcogenide glasses, photonic crystals, 2-dimensional materials, thin film solar cells, then photonic band gap materials, then nanoscale simulations, then biophotonics. And these are some of the major areas of research being conducted. And being one of the premier institutions in the country which offer photonics as a course, especially a 5-year integrated course, we are actively engaged in propagating the message of optics in society, and we do a lot of outreach activities every year. And speak in the year 2015-16 when we gave demonstrations and lectures at 100 schools in Kerala. But that is done every year, but it was a major event during 2015-16 when we were funded by Kerala State Science, Technology and Environment, and we have developed an optics kit at the cost of 3,000 rupees, wherein the school students can engage in basic optics related experiments in their school. And this is an ongoing activity. Coming to, in general, the optical sensors, we today make use of a variety of sensors in our day-to-day life today, whether it is in communication, biology, health, or in our home appliances. There are a lot of sensors that are being used every day. So it enables a contactless detection, counting, positioning, etc. A lot of tasks it can accomplish. The optical sensors are both sensors for light and sensors using light for sensing non-optical properties such as forces, displacements, tilts, temperature, velocity, pressure, chemical, or electrical properties. So a variety of non-optical properties, physical parameters that can be sensed using light. So they make use of light for sensing, and they are also sensing light. So one major category of a sensor is fiber optic sensors, and after the development of optical fibers and fiber optics and the communication using optics, the fiber optic sensors are gaining a large amount of attention in R&D. So in a basic fiber optic sensing setup, you will have an optical fiber, you will have a source, and you will have a detector. And in between, the light can be either extrinsically or intrinsically interact with the external medium or the parameters. These are all the measurements that we are looking for: the displacement, force, pressure, temperature, or any chemical species. So that is going to make some changes in the light that are propagating either in their amplitude or in phase. Those kind of changes are going to be detected at the output side. And so the major classification of fiber optic sensors are in this way, like it can be extrinsic or intrinsic. In an extrinsic fiber optic sensor, the light has to come out of the fiber, interact with the measurand or the analyte, then it has to re-enter the fiber, and that is how we will be able to detect any change in the magnitude of the light that is propagating. But in an intrinsic sensor, the light is, while it is being propagated through the fiber, it can interact with the measurand. So light can be inside the fiber while it is interacting with the analyte. So that type is actually known as intrinsic. Another classification is based on what parameter of light, what property of light is being changed with the interaction with the analyte. So for example, in some cases, you have the amplitude varies on interaction with the analyte. In that case, it can be intensity modulation, or it can the phase of the light propagation is actually affected. Then it is a fiber optic sensors based on this phase modulation, or there can be spectral modulation that can be also possible. The light that is propagating through the fiber will experience a spectral shift, a change in wavelength that is also possible. So this is a major categorization of fiber optic sensors. So the detector signal, optical detector used in fiber optic sensors depends on many factors like power emitted by the source, the coupling efficiency of the input and output fibers with the modulating element, because you have the measurements on, you have input fiber and output fiber. So how much coupling efficiency you have in this mechanism, that is eta, then the transmission efficiency of the fiber, then the response of the modulating element, and the responsivity of the detector. So the signal developed is a complex function of all these parameters. So in general, any waveguide actually supports the electromagnetic, distinct electromagnetic patterns. Like what is shown here is you have a waveguide like a plane parallel, which means you have a core region where you have the light is being propagated, and it has the cladding region as well. So the TAR is supported for certain angles. So when for a particular angle of incidence, which is greater than obviously the critical angle, some kind of constructive interferences are happening between these two beams after multiple reflections. For example, it has got a reflection from the point B, it is again getting reflected from point C, and then it is again traveling in the same direction. So these two waves, that the initial wave and the secondary wave, they are in phase. There is a constructive interference happening. So we can note that not every angle that is greater than the critical angle are not supported. Only some of them are resulting in a mode or a wave that are supported in the cavity. So the thing is that these particular angles which are permitted in the waveguide are actually known as, or they can lead to what is known as selected number of modes, and each of these modes have their own characteristics. And while coming to a analysis of these modes, they can be either treated as rays propagating at different angles, or they can be considered as electric field patterns, standing wave patterns in a perpendicular direction. So both are actually giving the idea of the modes. Okay, so for a particular angle you have a mode. So in that way you have three modes represented in the first figure. Similarly, another representation of the similar three modes is given in the figure below. So if you have an angle of propagation something like this along the axis, this is also permitted angle, like this black one. So it actually leads to a standing wave pattern within the electric field, within the waveguide structure. So something like this. It is a Gaussian profile, which is actually known as a fundamental mode. So this fundamental mode is actually not only confined, but it is actually penetrating slightly into the cladding. You can see a little portion of it is actually entering the cladding region. So that is actually something like a into a forbidden region. It is something like a leakage into the forbidden region, which is actually named as the evanescent wave. So if you consider a particular mode, it has a specific electromagnetic field pattern, a standing wave pattern within the waveguide with different values of penetration into the cladding. So if we compare the lowest order mode, which is a Gaussian, which corresponds to a ray that is propagating along the axis of the fiber. If you compare the penetration corresponding to this mode with a higher order mode, you can see that the higher order modes correspond to rays which are approaching the interface at a different angle, and they are entering more deeper into the cladding. So similar is the case with the standing wave pattern representation. So the higher order modes, of course, they penetrate more into the cladding. And why this is important, because many of the sensors, they make use of this property of light, that is the light leakage into the forbidden region. So it gives access to certain specific regions in some biology or in some chemical sensing applications, so that the light can go into certain specific region and interact while propagating through a different waveguide. So the light is being propagated, but at the same time it is able to interact with an analyte. And there are different mechanisms to do this, and one important way to do this is to remove the cladding. Okay, so once you remove the cladding, you have this evanescent wave, that is a light that is leaked out of the core, is having a direct access with the analyte. So this is an important method of fabricating sensors of very good sensitivity. So as we mentioned, this is the portion that is extending into the cladding, and once in this region for a certain length the cladding is removed, you have a direct access or a opportunity for the electric field to interact directly with the analyte. So in order to enhance the or improve the evanescent wave interaction with the analyte, there are a large number of mechanisms possible, allowed. For example, what is shown here in the top is the use of a tapered optical fiber, a fiber which is tapered, and this is the sensing region wherein the tapering means you have to heat the fiber and then pull it so that the diameter will decrease. So once the diameter is decreased, that means the field, so this is the field corresponding to the first mode. So this field is no longer confined in the core, because once this core diameter is reduced, a considerable amount of field is going to be outside the core. That means it is going to be evanescent. So that can be evanescently coupled to the sensing region or this analyte or the species, chemical species available here. So that is one method, the tapering of the core along with the cladding. So here you have a tapered tip. So you terminate the fiber tip, something like this. You heat and pull it and make a sharpened tip, something like this. This is a tapered tip. So this tip can also act as a sensing region, because at this particular location, the field is actually penetrating or leaking more into the surrounding region, and it can re-enter the fiber and pass through the same fiber to reach a detector. Similarly, you can have a sensing region coated with some specific coating, specific material. For example, in the case of biology, you can coat this tapered region or a low diameter region of the fiber using some kind of antibody, which can specifically bind to some antigens which are inside the analyte. So you have the analyte here in the sensing region and get attached to the antibodies that are coated over here. So that is another method. So there are a large number of configurations for the evanescent waves to couple or to interact with the analyte. And the last one that is shown here is very interesting, and most of our topic today, we will consider this kind of coupling, which means this is an optical fiber, that is some incoming radiation is coming through this optical fiber, and this is the tapered region. So that means heating and pulling of the fiber. So that means a lot of evanescent wave is going to leak out in this region, which will permit the light to be coupled to an external resonator. So this is a resonator, something like a capillary, for example, a micron-sized capillary through which some kind of fluid is flowing. It can be gas or it can be liquid that is flowing through this capillary region of the capillary. So this evanescent wave can resonantly couple into this capillary, and it will circulate in this curved region of the capillary. So light is actually getting trapped over here, and those particular modes or wavelengths which are getting coupled to this capillary or the micron-sized hollow structure will be absent in the output spectrum of the laser. So you have a source connected to the input side and an optical spectrum analyzer connected to the output side. So you can specifically see the light that are missing, or the wavelength corresponding to the wavelengths which are resonantly coupled will be missing in the output spectrum of such radiation. Another important type of sensor is the surface plasmon resonance based sensors, wherein you have the surface plasmons or the collective oscillations of the free electrons on a metal, which are excited by the use of a laser. So for example, you have a laser and this is a prism, and a metal layer is coated over here over the prism, and you are continuously changing the angle of incidence of the laser so that you are looking for the surface plasmon resonance angle. So at a particular angle of incidence, you find that the energy from the incoming radiation or laser is coupled resonantly to these oscillating electrons, and corresponding to that angle, your photodetector will show you a minimum reading. So from that angle, that means the surface plasmon resonance angle, its characteristics like FWHM, its actual position, how it is shifting with the surrounding dielectric constant will enable many of the biological sensing activities. For example, here you have a prism, you have a gold layer coated over it, and over that you have antibodies as a coating. You have antibodies as a coating. So in the analyte, you will have again antigens which can couple into these antibodies. They can get attached to antibodies, so which will effectively change the dielectric constant of the surrounding medium. So it is so specific, this dip that is observed here during this resonant coupling of energy from incoming radiation to these electrons oscillations is actually very sensitive to the surrounding dielectric constants. So you will be able to sense this kind of biological interactions very efficiently. So in Mach-Zehnder kind of interferometer is another type of sensor. So if we try to fabricate a Mach-Zehnder interferometer, implement a Mach-Zehnder interferometer in a lab on a table, it will require some, large amount of bulk optics like a laser source, then a beam splitter which can split light into two. Then you have additional mirrors, then again another beam splitter which can monitor the interference of beam. So for example, you have the two parts of the beam, and they are allowed, the two beams are allowed to interfere at a particular location, and you are able to introduce path difference in any one of the arms in a Mach-Zehnder interferometer. So in a Mach-Zehnder interferometer, a collimated beam is passed through a fiber optic coupler. So the same thing, this is on a table with bulk optics, and you will be able to sense, this can be used as a sensor by making use of, by making use of the phase change that is introduced in any one of the arms by considering one of the arm as the reference arm, the other arm is taken as the sensing arm, and you will be able to introduce something like a test cell or any object, for example, a refractive index measurement, or some gas pressure or something like that. That is to be introduced in one of the arms, the sensing arm. The other arm is unaffected, which is actually taken as a reference arm, and the corresponding interference patterns will be monitored at the output. So, but this is a bulk, interferometer. This can be very easily implemented if you consider an optical fiber interferometer, that is Mach-Zehnder interferometer implemented using an optical fiber. So basically, you have two optical fibers. One is sensing arm, the other one is a reference arm, and both are coupled through directional couplers. So you have a coupler. You have a coupler in the output side also, and your optical source is connected to one of the inputs, and obviously this coupler will split the light into two, and one is passing through the reference arm, the other one through the sensing arm, and it is again coupled through another directional coupler, and you have detector 1 and detector 2, and one a reference arm is actually completely isolated from external environment, but the sensing arm can be subjected to external parameters like strain, temperature, pressure, etc. And the corresponding phase difference that is introduced with this interaction can be clearly monitored by just measuring the detector outputs. So this is actually a very miniature version of the bulk optics that is used for the Mach-Zehnder interferometer shown on the fiber. So this is the advantage offered by fiber optics. Similarly, a Sagnac interferometer, which is actually a rotation sensor. So if you try to implement it on a table, it will require a laser source. Then you have a half mirror silver, which is nothing but a beam splitter. So it actually splits the light into two, both of them traveling in clockwise and anti-clockwise, but on the same path it is taking. Using the same path, the two light beams are propagating in clockwise and counterclockwise directions, and they are allowed to meet at the detector. And again, the phase difference that is introduced is actually measured while the entire setup is rotating in any one direction. So for example, if the complete setup is rotating clockwise and the clockwise propagating beam will take more time to reach the detector compared to the counterclockwise direction beam. So that way a path difference is introduced, a phase difference is introduced, and in the detector you will be able to detect that phase difference by monitoring the interference patterns generated. So this is a bulk interferometer, but this setup can be miniaturized for many space applications like gyroscopes, optical fiber gyroscopes. You just need a fiber coil, and the same fiber which is very small in diameter or in length or in weight. So you just need a beam splitter here, a laser source, and a detector. So the same fiber will replace all these mirrors and beam splitters, and it can be packaged into a very small size, and this is used in many of the space applications to measure the rotation. So the angular rotation of can be very precisely measured, and what is shown here is an example which can measure even the rotation of the hour hand of a clock. You can see considerable amount of phase difference between the two propagating beams. The clockwise and the counterclockwise beams can be generated simply by increasing the number of turns in the fiber. So you can think about maybe 10,000 turns. Not a single turn of the fiber is used, as 10,000 turns can be used. Still, the size of such gyroscope will be very, very small. So it can lead to a considerable amount of phase shift between the two propagating beams which are counter propagating. So in that way, it is very useful in space applications. And in fiber Bragg grating sensors, you have the gratings written on the core of the fiber by focusing some interference patterns generated from ultraviolet laser sources like XIII lasers. So the photosensitive core of the fiber is permanently modified to a periodic variation of refractive indices, something like a grating, and the fiber Bragg grating sensors actually work based on the principle of contra-directional coupling. So when light is introduced into such a device, this is an optical fiber with fiber Bragg grating written on it, then you will see that only a single wavelength will be reflected back, because it is a back coupling, and it's a coupling that is happening in the backward direction. So that particular wavelength, which actually satisfies the Bragg condition, will only reflected back. All other wavelengths will be transmitted, and you can either monitor a transmission spectrum on the output, or you can monitor the reflection spectrum at the input side, and more interestingly, this periodicity of the fiber Bragg grating is specifically you know changeable, or it can be changed, altered by the interaction with external medium like temperature, strain, pressure, etc. So even a slight change in these parameters in the surrounding region will change the periodicity. So depending on the periodicity, the reflected wavelength will be also different. And one advantage of this kind of sensing is that in the same fiber you can write a large number of gratings, same fiber. So you have a grating 1 with a certain periodicity, grating 2 with another periodicity which can reflect another wavelength, and the first periodicity grating is actually reflecting lambda 1, this is reflecting lambda 2, this is reflecting lambda 3, etc. up to lambda n. You can have n number of gratings written on the same fiber, and in the control room you can send a broadband light into such fibers, and selectively they can reflect depending on the strain or the pressure or temperature what they sense at that particular location. So the same fiber can be used to monitor the pressure variations or temperature variations happening at different locations, especially in a bridge or in a building, or in any industrial environment where the temperature has to be monitored from different locations on the same equipment. So this kind of distributed sensing is very much possible from. And one drawback of FBG is that the periodicity of the grating that is to be written is sub-micrometer. Like, for example, you have to write the grating with a periodicity with maybe 500 nanometer, for example. So that is extremely difficult. So that means any two successive high refractive index region has to be at a distance 500 nanometer or 600 nanometer. So that is very difficult, but a long period fiber Bragg grating, not Bragg grating, a long period fiber grating, which is known as LPG, can have periodicities greater than 100 nanometer, but the principle of operation is slightly different. Here, the coupling of energy happens from the core mode that is propagating in the forward direction to a cladding mode or to multiple cladding modes in the forward direction. So it is a forward coupling that is happening. So some of the modes are coupled from core to cladding, and if you closely monitor the output spectra, you will see some dips in the spectrum which corresponds to the energy or the wavelengths which are missing in the output because they have already been coupled into the cladding. So they are no more available in the output of the fiber. So you can easily have periodicities greater than 100 micrometer in this particular case. So coming to another class, which is whispering gallery mode microcavity sensors. So we will discuss more on this. So it is basically, as I mentioned, it is a cavity which is a mirrorless cavity. Why it is called a whispering gallery, I will explain. But generally, whispering gallery modes are monolithic dielectric optical cavities or optical resonators. They are monolithic dielectric structures because in most basic geometry, they will look like a sphere, for example, or it can look like a toroid, or it can look like a ring. There are many structures for whispering gallery mode. We will discuss that, and some of them are shown here. For example, this is a toroidal kind of structure or a ring-like structure to which the light can be coupled evanescently using an optical fiber which is tapered. So you have a light source, you have a detector, which can be connected to a spectrometer as well. So you are monitoring the output spectrum, you have an input laser, and in between you are allowing the light to couple out or to leak out of the fiber because this region is tapered. So a large amount of evanescent wave is actually available, and that can be coupled into this whispering gallery modes like that cavity, WGM cavity we call it, whispering gallery mode cavity. It can be circle, it can be toroid, it can be ring-like structure, etc. So somehow if you couple such energy into such cavities, they don't have, you can see they don't have any mirrors, but without the presence of mirrors, they can efficiently recirculate or resonate within the cavity by the principle of total internal reflection, because you have refractive index difference at this interface. This is a high refractive index region, and this is a low refractive index region. So they can efficiently recirculate for a longer period of time. As I mentioned earlier, the measure of the efficiency of any microcavity, WGM microcavity, depends on its Q factor. The Q factor, the larger the Q factor, you will have a longer period of time the light will recirculate within the cavity without losses. So ideally, the losses are there, but you have to make sure that your light is recirculating or resonating within the cavity to comparatively longer period of time. So the measurement or the measure of such a property is by measuring the Q factor of the cavity. So there are different ways of coupling light into such microcavities, using a prism, using a polished fiber, or using a tapered fiber. The tapered fiber we have already discussed in the last slide. So the WGM cavity can be excited, or the light can be coupled into the cavity using a prism like this. You can choose a particular angle at which the light is coupled to maximum, and the leaked light can be efficiently confined in the WGM microcavity. Similarly, angle polished fiber, similarly the tapered fiber, all of them are actually generating or leaking out light that is actually coming out of a fiber. So for example, what is shown here is in a biosensor. As I mentioned earlier, if you have a spherical WGM cavity, something like this, this is actually made up of a optical fiber, silica optical fiber. So if you have the fiber tip and if you are able to heat it, the temperature, I mean, in tune of 2000 degrees, you will see that the silica optical fiber, they start melting, and at the tip of the fiber, you will be able to generate this kind of spherical structures. And if you are able to attach some kind of antibodies onto the surface of this spherical WGM cavity, and you can efficiently couple some kind of radiation by a tapered fiber. So this is a tapered fiber which can which is used to couple light into the spherical WGM cavity, and it efficiently resonates here, and at the same time you have antibodies attached to the surface of this sphere. So you are then monitoring the output spectrum of your optical fiber output. So you can clearly notice that the light that is being coupled, or the wavelength that are coupled into the WGM cavity, will be obviously missing in the output spectrum, but it can monitor how the antigen antibody are getting binded, and what is its rate, and the similar chemical reactions or biochemical reactions happening in any analyte can be directly monitored. Simply monitoring the shift in the optical transmission spectrum here. So you can see the dip can be varying from lambda 1 to lambda 2 depending on the surrounding dielectric constant change which happens due to the binding. So there are different parameters for a sensor. I'm not going to details. I will just list out sensitivity, detection accuracy, limit of detection, selectivity, then response time, resolution, repeatability, reproducibility, noise, dynamic range, linearity. So it is very important that a good sensor should have a linear calibration curve so that any unknown value of the analyte can be very easily found out from such a calibrated curve. So the drift, then reusability, shelf life, figure of merit. So these are the general parameters in order to analyze the performance of a sensor. But I'm not going to the details of that. You sometimes may be aware about the electronics and the noise aspect of a detector, etc. Some of you may be from electronics background, which is very common to any detector used in optics. So coming to the use of some fluorescent material. So far we have seen why a WGM cavity is used and how light can be coupled into such cavities. But now I am introducing a concept of fluorescent materials, so which are very widely used in a range of applications, including in microscopy, for example. So you can use quantum dots, you can use organic dyes, a lot of materials, rare earths, a lot of luminescent materials available, a variety of wavelengths and colors. And in biology, they are used for staining. For example, if you look through the microscope and observe a biological cell or structures, you will not be able to distinguish different parts of a cell because the contrast will be very less. But after staining it with some particular organic dyes, you will see that the different portions of the cells or the biological structures can be very easily distinguished because of the specificity of these molecules which get attached to certain locations of the biological structures. So that is actually very much useful in fluorescent microscopy like this one. So if you stain such biological structures and then look through the microscope, it will be looking like this. So it is very easy to distinguish any anomalies in the structures or dynamical changes happening at certain location. So all these can be very easily found out. But there are problems as well, because many of these emitting structures like luminescent probes, they emit wide range of wavelengths. So you cannot use a large number of a variety of luminescent probes simultaneously, because each of them are emitting a range of wavelengths, not a single wavelength. That is a challenge. It is also fundamentally challenging to engineer molecules with much narrower spontaneous emission. And also it is very difficult, or it is not a easy challenge to confine their emission range to certain minimum narrow width. But there are possibilities like stimulated emission. So you can think about structures, for example, dielectric structures doped with this kind of fluorescing material, and then allowing them to emit light in the form of stimulated emission like laser, not just fluorescence. So what is shown here is just a fluorescence. When you shine light on them, they absorb energy and then they re-emit energy in the lower energy side. So that means if I excite these structures with a certain wavelength lambda, they will absorb it, and the molecules get excited to a higher state. Then they will de-excite non-radiatively. That means they are going to lose a lot of energy in the form of heat mainly, and they are going to emit a little energy. That means compared to the absorbed energy, the emitting energy will be lower. So that is actually what is called the fluorescence, and this emission is not directional. It happens in all the directions. It is not coherent. It is not monochromatic. So in that way, you have problems in collecting this radiation. But you consider the stimulated emission happening from such material. For example, these fluorescent materials or luminescent probes doped in structures like WGM cavities. So these are cavities without any mirrors. They can recirculate light efficiently. So if that medium is also having this kind of fluorescent probes, it is highly likely that the stimulated emission will generate lasers out of such structures. So laser is obviously going to be having superior properties, coherence, monochromaticity, and directionality. So this is just a comparison. You take a fluorescent material in a cuvette, excite it. You take a laser-based mechanism wherein you take the same cuvette, same material, but you have an optical feedback. That means the same is placed in a cavity. That means between two mirrors. So both are excited. You can monitor the emission. The first one is just going to give you a spontaneous emission, that is emission in all directions without any directionality, and you have emission according to the input radiation. So the pump energy you increase, you just get the increased emission. So that relationship is going to be linear, and it is going to emit a broad excuse me. A broad emission spectrum. You can see, for example, 50 nanometer is the emission happening from such a fluorescent material when it is excited without the presence of a cavity. But the same thing you can compare here. You can see that the input intensity is increased, that is the excitation intensity is increased. You see that beyond a threshold, it is actually shooting up. The intensity is going to shoot up. So you can see that this is actually the lasing, or the signature of lasing is the existence of a threshold energy, input energy. So beyond that, it is actually shooting up. The energy is shooting up, and you can see that it is going to be directional. It is going to be monochromatic. Something like you can see that you can compare the emission ranges of a spontaneous emission and a stimulated emission. So you have stimulated emission, directional emission, you have nonlinear threshold behavior. It's no longer a linear behavior of the input and the output. It is nonlinear, and the spectrum is much narrower, and very good signal to noise ratio, better spectral and spatial as well as temporal characteristics of the emission. Laser emission is in one or more preferred direction, and more interestingly, this is going to give you a directional emission compared to the 360-degree emission happening from a fluorescent signal. And there is a threshold behavior. The spectrum is narrower by several orders. You can compare the spectra. The laser output characteristics can be sensitive to biochemical changes, leading to changes in the refractive index and gain. And this can be also used for sensing many parameters, biological and physical, chemical parameters. If your material is emitting a laser, something like this, that is stimulated emission, is happening from your sample, that is going to be very much sensitive to the chemical parameters or the biochemical changes or any physical changes in the vicinity. So the optical microcavities basically make use of, or it exploit all these properties of the cavity emission. That is, the selected frequencies that are circulating in the cavity. They are very much sensitive to the surroundings. So this is the principle used by the optical microcavities. So it is acting as a tool to trap the light by resonant recirculation, and it can be applied in lasers, it can be applied in filters, it can be applied in sensors and switches, etc. So an ideal microcavity or optical cavity should confine light forever. Practically, it is described by the term Q factor. So there are a lot of biological and man-made resonance systems available. It need not be the optical microcavity. It can be mechanical vibration, or it can be some acoustic sources which actually recirculate at certain location. So if you compare many such biological and man-made resonance systems, you will find that the optical microcavities are having a large value of Q factor. So in fact, it is possible to create Q values of the order of 10 raised to 10 compared to all other classes of resonance systems available in the nature. So optical microcavities are superior to all other type of microcavities. So how to confine light? We have already mentioned that you can confine the light in a microsphere. You can use a tapered optical fiber to couple light into that. But the most basic systems confine light in a simpler way, something like you have two plain parallel mirrors and you couple light into that, and this light is allowed to resonate for a large number of times because they are perfectly aligned and they have very good reflectivity, etc. And this type of mirror cavity is basically known as the Fabry-Perot cavity. So a microcavity can be Fabry-Perot type, or it can be WGM type. As we mentioned earlier, it is a spherical dielectric monolithic structure which can efficiently recirculate light. That is WGM. Or it can be distributed feedback microcavity, something like this. So distributed feedback means it is having some corrugations or periodic refractive index variations across a length or along a particular length of the device, which can spectrally purify the light that is propagating through this waveguide. So this is basically a waveguide with a corrugated structure on one side. So some spectral purification and efficient filtering process is happening in this kind of distributed feedback microcavity. And the fourth one is photonic crystal cavity. The photonic crystals, they have periodic refractive index variations in either 1 dimension, 2 dimension, or 3 dimension, which will prohibit the light of a specific wavelength because of the photonic crystal effect. So just like in an electronic crystal, you have the band gap wherein electrons of certain energies are forbidden because of the periodic potential of the crystal. So for example, the silicon or germanium, it offers a certain value of band gap. It actually arises because of the periodic potential available in the lattice of the crystal, and through which the electron is trying to move. The electron finds a range of energies which are forbidden. Similar fashion, you have the dielectric that is varied periodically, that the dielectric constant or the refractive index of the material is periodically varied either in 1 dimension, 2 dimension, or 3 dimension. So a particular wavelength of light is not permitted or totally prohibited. So in such structures, if you create some kind of defects by purposefully introducing a defect, means you have to either remove some amount of these holes. For example, this is a structure with a planar structure with some holes in it. You can imagine this as a glass with a large number of holes drilled into it periodically. So you can imagine at certain location you have created a crystal defect by removing the air holes. You have perfectly glass over some region, so that acts as a defect, and the light will be perfectly confined in that region because it is permitted in that region, but in no other region it is permitted. Actually, it is forbidden. So you can have a different integrated circuit, photonic integrated circuits, which can bend the light even through very impossible angles when we compare it with the optical fiber propagation. So in optical fiber, if you bend the fiber beyond certain angle, what happens is at acute angles the light is totally lost from the fiber. The losses are very high, but you can create even perpendicular bending of light. That 90-degree bending of the light you can think about in a photonic crystal. So these are the ways in which the light is being confined in normal microcavities. This is the basics of fiber Fabry-Perot interference like cavity. This is basic optical resonator that we study in lasers. It will have two plane mirrors, and the light is coupled into the cavity from one side, because this is a partially silvered mirror, and this is also a partially silvered mirror, and the light is allowed to recirculate within the cavity, because after complete round trip, if the path is an integer multiple of lambda, or the wavelength, that wavelength is going to be, or those waves will be efficiently recirculating by constructively interfering with each other. That means some kind of filtering process is actually happening between these two reflecting plates, and you have only selected number of wavelengths which obey this condition for constructive interference will be available in the output. That means they efficiently recirculate, they increase in intensity, and since it is partially reflected mirror, you can see that only selected number of wavelengths or frequencies are available at the output. So it can act as an optical filter. Only certain wavelengths are only transmitted. But even though this is very easy to construct, like this is easy to imagine conceptually, because this requires only two plane mirrors for this confinement or for this filtering, it is very difficult to implement, because it requires high reflectivity of the two mirrors, and the alignment has to be perfect, and the very short cavity length is required, so that you will have a considerable amount of spacing between the allowed wavelengths. So if the spacing is large, you will find that a large number of these selected frequencies, they will come very close to each other. That means the free spectral range, that is the spectral range which is free of any wavelengths. That means this is a free spectral range. For example, you have nothing in between these two wavelengths. So this will be very small if you increase the separation between the cavities. So in order to identify or separate at the output, to have a very small spacing between the two mirrors. That means the shorter cavity length is required. Also, the reflectivity of the two mirrors have to be very high. You can see what is the effect of reflectivity on these selected frequencies. So if the reflectivity is around 80%, you have clear, distinct frequencies selected. And once it is reduced to 40%, for example, it is actually coming closer and closer. So smaller and smaller reflectivity will not allow you to distinguish between these two a number of frequencies that are selected. So that is the problem with this kind of Fabry-Perot cavities. But coming to whispering gallery mode, its name actually originates from the St. Paul's Cathedral, London. This is the cathedral in London, and it has a dome over here, and this is the inside view of that dome. This dome has this is a very huge dome with 32 meter in diameter, and you can see that people are actually walking through this dome, and they can sit over here and they can speak, they can whisper towards the wall, and it can be clearly heard on the opposite side of the walls. Okay, so it's a 32 diameter circular gallery under the dome. Even a small whisper from one side is clearly audible at the opposite end. So that means you can imagine something like this dome, and the sound waves, they can resonantly recirculate and complete a cycle, and it can circulate something like this without much losses. That is why at different location you will be able to hear the sound very clearly, or what the other person is whispering. So this is the acoustic variant. It was explained in 1878 by Lord Rayleigh, and he proposed this name whispering gallery modes for acoustic waves in the Cathedral of St. Paul's in London. But later in 1908, Gustav May actually explained this phenomenon for optical wavelengths, and he explained it using the scattering spectra of the plane waves from small spherical particles. So when you have dielectric particles or spherical structures, the light can also get recirculated resonantly in these structures. That was explained in 1908. So this is the electric field mode distribution representation of a whispering gallery mode optical cavity, and this is a spherical whispering gallery mode cavity. So why the WGM cavity? As I mentioned earlier, the state of the art required for the Fabry-Perot resonator, the two plane mirror cavity, even though conceptually is very simple, they requires the state of the art for fabrication, because high value of reflectivity is needed and the alignment of the mirrors is very important. Its Q value is, the quality factor is limited by the imperfections of the dielectric coating and the substrate polishing, and large scale experiments that is very much difficult to commercially manufacture that kind of plane parallel mirrors without imperfections. So this is just a comparison between the Fabry-Perot cavity and WGM cavity. You can see this. It needs to decrease the cavity size to allow strong confinement, needs to increase the reflectivity of the mirrors for reducing the optical losses. Q factor is limited by the quality of the mirrors. These two are two curved mirrors that is shown. But in the WGM cavity, you have the high Q values, as we mentioned earlier. It can be as high as 10 raised to 10, and its size is very small. The mode volume, the volume over which the light is confined is actually very small, which can be directly applied to many biological and chemical sensing applications. Narrow spectral widths, resonant condition is this one. That means this circumference of the sphere, for example, circumference, and multiplied by the refractive index, that is 2 pi r times the refractive index, that is the effective refractive index of the mode that is circulating, should be equal to an integer multiple of lambda. That is the simple condition required for the resonant recirculation of a particular wavelength in this structure. And the Q is limited by surface quality and absorption. It is not depending on the mirror quality anymore, because we don't use any mirror here. So the high reflectivity over broad wavelength range, you take a broad wavelength range, lambda 1, lambda 2, lambda 3, etc. You will find many of them are circulating within this cavity, because the reflectivity is therefore offered for a wide range of wavelengths. Coupling is by evanescent coupling. So it is something analogous to quantum tunneling we already mentioned. If you have a tapered optical fiber, very easily you will be able to couple light into such resonators. Coming to the micro resonators again, why they are used? They can be used for a variety of applications. They can be used as a switch. They can be used as a resonator. They can be used for optical coupling as well. So this is actually a representation of a switch. So that means creation, transition, and termination of connections is possible in electronics. In a similar fashion, in a micro resonators also, it can act as a switch. It can also act as a resonator. What a resonator do? A resonator reinforces a frequency of a waveform like sound or light. If you have a signal, it can be sound signal or a light signal. If you have a resonator, then it will reinforce and select a particular frequency out of the input signal. So it can do that very effectively. You can have only selected number of frequencies available from a resonator. Similarly, optical coupling is also possible because we mentioned earlier that a light can leak out of a waveguide whenever you have a smaller diameter or a tapering of the optical fiber is possible. So you can see such a device which is actually a directional coupler shown here. So you have one optical fiber to which light is coupled. You have another optical fiber sitting very close to that, and these are, you can imagine, like a tapered region, or they are sitting very close to each other, wherein the evanescent wave from the first fiber is able to leak into the second fiber core, and you can end up with a coupling of light from the first fiber to the second fiber. So depending on the coupling parameters, it is ideally possible to couple 100% of energy from the first fiber to the second fiber, or you can have 50-50 coupling or 20-80 coupling, depending on the coupling conditions like separation between the two fibers. Have you removed the cladding of the two fibers, or are you allowing enough length for the interaction to happen? So controlling these parameters, you will be able to generate light splitting. That's what I call it. You can have a 100% light coming from here. You want to couple it into equally into two fibers. So you can make use of this kind of couplers. So how this micro resonators coming into picture here, you can see, for example, in optical communication, you may use add drop multiplexers like this one that is shown here. So conventional add drop multiplexers use an optical circulator, a fiber Bragg grating, then a second optical circulator. So that means you have a circulator is a 3-port device in which the light enters the circulator, will come out of the next port, but it can act only in one direction. It's a unidirectional device. It's a 3-port device. So that means if the light is entering from here, it will exit from this port, next second port. And if it is entering from here, it will exit from this port. So in this fashion, if you want to take out any particular wavelength, you have n number of wavelengths like 1, 2, 3, 4. And after traveling through the optical fiber, suppose you want to drop out a channel. So each of these wavelengths representing a channel, and you want to drop out a channel. What is done here is you allow a circulator here, circulator actually couples the light in, and then it gives out, or the light actually goes out through the next port. It enters a fiber Bragg grating. A fiber Bragg grating is a periodic refractive index variation that we have seen earlier, which will reflect selectively a particular wavelength depend on the periodicity. So this particular lambda is actually dropped here. That means it is actually getting reflected towards the circulator itself. But circulator is a unidirectional device. It will allow the light to drop from the very next port. So it's a 3-port unidirectional device. So suppose I want to add another channel from this location, and I want to couple that particular channel and allow that wavelength to travel along with the already existing wavelengths to a certain other location. I can also add a separate wavelength from here by making use of a circulator FBG combination here also. You can imagine something like this. A circulator is a 3-port unidirectional device. It can enter here, it can exit from here, and it can get reflected from the FBG, and it is again coming here. Again, it will exit through the circulator. So in that fashion, a new channel can be, or a new wavelength can be introduced. At the same time, another wavelength can be dropped. This is the conventional way of implementation of add-drop multiplexer. But in the case of a microresonator, you can keep a microresonator in between 2 optical fibers, for example. And if you make a slight tapering, for example, here, or even otherwise, if it is in contact with the microresonator, and if the coupling conditions are ideal, you will be able to couple a single wavelength into this just a moment. So you will be able to couple light out of one fiber into the microresonator, and you can drop that one to another fiber. That is actually possible. So any optical ring resonator can redirect light. Specific frequencies get redirected, or we can say it filters them, and the size change with thermal expansion. So the size of the microresonators can be controlled thermally. So if you have a mechanism to slightly vary the diameter of this microresonator, you will be seeing that a different wavelength will be coupled and dropped out from such a mechanism. So, and this kind of sensing also we have already mentioned in a biological sensing, antibody antigen interaction we have already mentioned. So a WGM microresonator being monolithic circular dielectrics, they rely on total internal reflections rather than dielectric mirrors. It doesn't require any mirrors. The Q factor is determined by the surface quality. You have to improve the quality of the surface of the cavity, and we are not making use of any mirrors. High reflectivity over broad wavelength range, we have seen earlier. Coupling is using some kind of quantum tunneling mechanism using a tapered optical fiber that we have already mentioned. Now, coming to practical applications. From now onwards, we will focus on some practical applications of these micrometer sized cavities, and we will classify them into active and passive cavities, and I will come to that. Before that, I am just showing you a liquid droplet. You have a droplet generator. Okay, yeah, these droplets are generated from the top, and from the bottom you have a laser is focused on to this region, and you can see that the gravity can be completely balanced by this laser beam, and it is something called the optical levitation. So this is a setup for experimental setup for optical levitation, and the droplets are generated from the top, and it is actually levitated using a laser from the bottom, and it is actually studied. Its spectra is actually monitored, its dynamics is actually studied, and you can see that if this droplet is emitting light, this droplet is actually acting as a microsphere or a microcavity, and the light that is getting trapped into that can be used for many kind of sensing applications. You can see the quality factors of the order of 10 raised to 8 and 10 raised to 9 can be obtained from liquid carbon disulfide and liquid hydrogen droplets respectively. So liquid hydrogen and liquid carbon disulfide can be used for generating these droplets, and those droplets can have quality factors of the order of 10 raised to 8 to 10 raised to 9. So what is shown in the schematic diagram is a levitated micro drop of the picture inset that is shown here is the micro drop containing CDSE ZNS nanocrystal quantum dots. So the droplet, if it contains quantum dots like CDSE, ZNS, etc., it will act as something like a laser, a micro laser. You can see that micro laser out of this micro droplet is actually imaged using a CCD and is shown here in the figure. Similarly, coming to biology, there are a large number of micro droplets available in some cells naturally, or you can introduce these kind of micro droplets into the cell by injecting into them. So for example, what is shown here is the lipid droplet that is available in a cell, and if you are able to incorporate some kind of fluorescent material into this cell, and you couple some light into this, you will see that this is the pump energy, that is the input energy, and the output. If you monitor that, you can see this clearly monitor this nonlinear behavior. That means the input energy is increased, the output energy is non-linearly increasing with a threshold behavior, which is a signature of lacing. So you can monitor the light that is coming out of such a biological cell and plot in a spectrometer. So with a high resolution, we can see that certain frequencies are actually circulating, and they are very narrow width. They are lasers actually. So they are stimulated emission is happening here, and selected number of frequencies are actually circulating, and because of the presence of fluorescent material, it acts as a laser. Similarly, you can put solid microcavities like polystyrene beads into certain cells, because the cells, if the beads are up to the size 20 micrometer, some of the cells like macrophages, phagocytic cells, they can readily internalize. So this is a cell, and this is the bead, that is the polystyrene bead. So if it is very close to the cell can automatically internalize this the bead, and the bead is actually having a fluorescing material, and you shine light on them, you can see that it laces. The emission spectrum is actually monitored using a spectrometer. It contains specific wavelengths, and more interestingly, many activities, intracellular activities like changes in pressure, strain, pH value, all of them that are happening inside a cell will be reflected or can be used to change the output spectra coming out of this bead, fluorescent bead. So this fluorescent bead actually goes into the cell and monitors all the internal dynamics of the cell. Now, coming to silica based WGM resonators, Though you can, as I mentioned earlier, if you heat heat and melt a optical fiber tip, it will look like this. So it can this sphere, this spherical end of an optical fiber can very well act as a microsphere and a WGM cavity. And what is shown here is a microsphere and a microfiber, then a microtoroid. So this is a toroid through which the light can circulate efficiently. And this is a capillary, a microcapillary, a micro disc, and a split disc, a disc with a gap in between, then a micro bottle. That means on either side you have smaller diameter, and in between you have a larger diameter, that is like a bottle-like structure, and a ring resonator. There are a large number of geometries available for WGM resonators based on silica. And there are polymers used for this kind of resonators as well. That is, this is a PMMA, polymethyl methacrylate micro goblet lasers fabricated by parallel solution based processing. This is reported in 1915. So you can see that this is almost looking like a toroidal kind of shape, but it is fabricated periodically in a large scale by solution based processing. So the PMMA, if you compare with the silica material properties, there are a large number of advantages possible for PMMA, because the large thermal expansion coefficient, because many of these microlasers are going to be used for sensing temperature. Okay, so in that case, the thermal expansion coefficient is almost 2 orders of magnitude larger for PMMA. And the Young's modulus, you can see it is flexible material. The elastic limit, you can see it is large. It will not break very easily. Handling is very easy, unlike the normal optical components made of silica, which is easily damaged. And also the thermal expansion coefficient as well as the thermo-optic coefficient, they are both almost 2 orders of magnitude larger. So now we make use of some optical fibers. So not the toroids, not the spheres, etc. What happens if you make use of some optical fiber structures in the micrometer size, and then if this optical fiber can trap light, something like a microcavity, can it be used for sensing applications? Because we already know a large number of benefits that are offered by optical fibers in data communication, and then other biological, medical applications. This very small diameter dielectric structure, either it can be plastic or it can be silica, they are directly in use, and the technology is well evolved. And why can't we use such optical fibers made out of polymers, silica, etc. for creating this kind of micro cavities, WGM micro cavities? And moreover, the polymer optical fibers, they also give a large number of advantages compared to the silica optical fibers. Some of them we have already mentioned, that the thermo-optic coefficient, larger thermo-optic coefficient, and also the thermo expansion coefficient is larger. And most importantly, the processing temperature of polymer based optical fibers are much smaller. That is almost 10 times smaller compared to the silica, because the silica, the processing temperature is 2000 degree compared to a 200 degree of polymer optical fibers. So it is very easy to fabricate and handle, and also it offers minimum losses around the visible wavelengths. So if you compare the silica property, the minimum losses for silica is happening in the infrared, like 1.3 micrometer, 1.5 micrometer, etc. But here in a polymer material, you will have the minimum losses happening in the visible region, that is the visible region of spectrum. You will have a minimum attenuation or losses offered by polymer. So you can use this kind of material for fabricating fibers which transmit light in the visible region, or you can transmit visible light through this material and you use it as a sensor. So basically polymers deals with visible light while silica deals with infrared. So you can do this experiment in the lab by incorporating many fluorescent materials available in the market. It can be quantum dots, it can be nanomaterials, it can be organic dyes, fluorescent dyes. So you can incorporate them in solution form, it can solidify into rods, and you can draw it as optical fibers in a optical fiber drawing mechanism. And you can also try different combinations. For example, this particular plastic material or PMMA organic material, it can pump using a blue laser, and you can expect green as well as red emission out of this PMMA material. This is actually doped with rhodamine and coumarin. Both are emitting at different wavelengths, and basically you can expect multiple wavelength lasers. So by drawing them as optical fiber in a optical fiber drawing machine, you will end up with optical fibers with the same quality or the same property. So the blue excitation, for example, you will get two emission wavelengths. You will have a green emission as well as a red emission. So, and it is more likely that these are lasers, not the spontaneous emissions, because once you draw them as optical fibers, their diameter are going to be just like 100 micrometer, 150 micrometer in diameter, which is very much can be called as a optical microcavity. So they doesn't require any mirrors for optical recirculation, so they can act as efficient lasers. So basically, if you have a plastic optical fiber with multiple dyes or quantum dots doped into it, you have multiple lasers coming out because they are actually efficient micro cavities which efficiently recirculate to different wavelengths. So that is one experiment that is being done here. And the other one is the photonic crystal fibers that is widely researched all over the world. And you can see here the cross section of two photonic crystal fibers generally used. This is one having effective refractive index guidance, and the second one is photonic crystal guiding or photonic band gap guiding. So in the first one, you can see this is a cross section, that is the air holes are running along the length of the fiber, and this is a defect that is created at the center. That means one hole is actually missing, which means it can act as a defect and the light can be confined through this region, and this mechanism is actually called the effective index guiding. And the second one is you have again the periodic refractive index variation, but you have again a defect over here. That means the defect is something like a large diameter hole compared to the others. So all these region, it is photonic band gap existing, and this is the region where it doesn't exist or it is a bigger air hole. So in the second case, the light is going to travel along the hole. That means the light is not going to interact with the dielectric medium at all. It is mostly confined in the air hole. So this will be useful in transporting huge amount of energy from one building to the other building, one location to the other location, because the light is essentially not interacting with the glass. It is essentially contained in the core because of the photonic band gap effect, because these are dielectric structures which are periodically arranged, wherein the lambda that we deal with is experiencing a band gap. So it is not obviously permitted in this region. It is actually going through this location only. But we also tried to fabricate. This kind of optical fibers in our laboratory, but not successful so far because it requires much more expensive experimental setup. It requires much more sophistication. So we were not successful, and some of the figures that are shown on the right hand side shows the fibers that resulted from our attempts. You can see most of them are without any periodicity. Many of the holes merged together, and it was not quite successful. But what we found was, in order to make these fibers, what we did was we fabricated many hollow fibers, then stacked them together, and then they were again drawn. So while doing so, we found that it is not very easy to fabricate photonic crystal fibers in our laboratory, but individual hollow optical fibers, when doped with some organic dyes, they acted as lasers while exciting with while excitation with another laser is done. So basically, this is a hollow fiber that is shown here, and this hollow fiber is a material of PMMA. It is basically dye-doped PMMA. So a fluorescent material doped PMMA fiber with a hole. So what we found that this can act as a microcavity. It doesn't require a mirror. When you shine light on them, it efficiently recirculates, and the resonance creates laser emission. Okay, so you excite with a green laser, it is actually giving something like an orange laser, this particular hollow optical fiber. So the mechanism that is happening here can be explained something like this. This is a cross section of the fiber, a hollow fiber which is doped with a red fluorescent dye. You can see the light is efficiently recirculating inside such a fiber cross section, you can see. And this is the gain medium because the fluorescent material is also there. So you can actually calculate the lambda spacing. So of course, these efficient recirculation or the resonant recirculation is only possible for selected number of lambdas. So what are the lambdas and what will be the spacing between those lambdas can be easily calculated by this expression, where d is this diameter and lambda is the emission wavelength and the peak emission wavelength, and delta lambda is the separation between the emitted wavelengths. NP is the effective refractive index of the modes. That means it is related to the refractive index of the core, I mean the plastic material and the surrounding material. So it can be calculated. Now you can see this is a hollow optical fiber through which a flow of the fluid is happening, for example. So this is the hollow region of the capillary, and this capillary is acting as a WGM cavity. So, and some kind of gas or liquid is actually flowing through the cavity. So some way this cavity is actually doped with, made of silica doped with erbium, ytterbium, that is rarer. The rarer elements erbium ytterbium combination is doped in this silica capillary, and we are pumping it using a tapered optical fiber at 980 nanometer. So this incoming radiation is 980 nanometer, and this region is a tapered region. So it can, the evanescent wave can be leaked out of this tapered region, and it can be efficiently coupled. So the WGM resonance is happening in such a capillary. So this fluid is also flowing through this capillary or the whole of the capillary. So now what is important here is that this can act as a temperature sensor because this circulation of WGM is actually locally heating the capillary. So this efficient circulation of WGM is locally heating the capillary. So then the temperature is slightly higher in this region, and when the fluid is actually flowing and you are actually monitoring the output of the fiber through a optical spectrum analyzer, you will notice that the wavelength that is actually coupled into the microcavity will be missing in the output spectrum. So you will find dips in the output spectrum. But now you find that the fluid is started moving. Okay, so when the fluid is started moving, it will take away the heat energy in this location to some other location. So obviously the temperature will come down in this location. So the surrounding temperature comes down. So it will effectively change the refractive index of the region, and in that fashion the dip will be shifted to some other frequency. So that means you have a shifting in the WGM coupled wavelength while monitoring the transmission spectrum is very much possible, and this is acting as a hot cavity anemometer because the fluid is flowing. The rate of fluid flow can be directly measured, the temperature changing can be directly measured, and this is a work that was reported in 2016 by Jonathan M. Ward. And there are two types of WGM sensing mechanism. One is the passive WGM, the other one is the active WGM. So the passive WGM, you have a tapered optical fiber in contact with a cavity. So this cavity is a cylindrical cavity, for example. So this is a broadband light source. A white light source is actually coupled using a tapered optical fiber to the WGM cavity. This is a cylindrical WGM cavity, something like a optical fiber. And you monitor the output spectrum, you will find dips in the output spectrum. So this doesn't contain any fluorescent material, so this doesn't act as a laser. But in an active WGM, the WGM cavity is topped with a fluorescent material, and when you couple light from an external source, like a laser source is actually directly allowed to fall on this cavity, you will see that the coupled radiation act as a laser. Coupled radiation into the microcavity builds up to a lasing modes. So these are the modes that are generated. So you can directly monitor the emission that is happening from this this microcavity. It is actually a laser output, and it is basically depending on the surroundings. It can be heat, it can be pressure, it can be other pH variation, refractive index variation of the surroundings of, suppose it is immersed in a liquid, etc. So these laser modes are going to be shifted according to the surrounding variation of the surrounding. So in a passive WGM, you will have dips in the transmission spectrum, and in an active WGM, you will directly monitor the emission that is happening from the cavity, because the cavity itself is going to act as a laser, and it is going to emit some frequencies that will be clearly monitored in a spectrum. So these are some of the experiments. You can you have a passive WGM laser source, a spectrometer in which the dips are monitored, because those dips are corresponding to the wavelengths which are coupled to the cavity, microcavity. So you can have coupled polymer microfiber lasers also. You can have one microcavity sitting here, polymer, the other polymer fiber microcavity is sitting here. So one is excited, the emission is happening from the one only. And if you consider both of them are sitting very close to each other, so you can have a coupled cavity. So you have a resonant condition for the first fiber cavity, you have resonant condition for the second fiber cavity, and the total emission for the coupled cavity will be different. So this is one method of modulation or selectively obtaining certain modes from the WGM cavity, because this will have a set of wavelengths emission. This is also having another set of wavelengths of emission. But when they are combined, you will have only a very few number of wavelengths which will satisfy the condition for the resonance for the first one and the second one. So you can have selective mode excitation possible, and the refractive index sensing using this coupled cavity is comparatively better. Another way of doing the same experiment is by you take a hollow cavity. That means a hollow fiber in which in the inner wall of the hollow cavity is only doped with some active medium like a fluorescent material. So this fluorescent material is acting as a laser only in the inner region. You can see the same image. This is the hollow fiber, and the inner region only acting as a laser. You can see this laser coming out. You can monitor this output, and this can be very effectively used for sensing strain, because if you extend this fiber while lasing, the diameter is going to change, so the circumference of the circle is going to change. That the circumference of the circle will determine the emitted wavelengths. So in that way, this is going to be a very good strain sensor. Similarly, the refractive index sensing can be done, because if such a fiber which acts as a laser, this microcavity, it acts as a microcavity, it acts as a laser because it has a fluorescent medium doped in it. Now this is immersed in a liquid and it is excited with a green laser, and it emits orange color radiation, but with the change in surrounding refractive index of the liquid in which it is immersed, there is a shift in the wavelength that is generated by this microcavity. So in that way, it acts as a refractive index sensor. Though when we extend this fiber cavity, microcavity, it can act as a strain sensor. And this is a packaged polymer optical fiber based strain sensor, because the packaging is very important in any kind of sensor devices. And it can also thermo-optic tuning also possible. You can, while it is lasing, while the cavity is acting as a laser, you can shine another laser onto the fiber so that it can be locally heated. So that local heating actually generates the temperature variation, and temperature tuning can be very easily implemented in such devices. And also, not only the lasing, just the fluorescence that is coming out of such devices can be monitored with some temperature changes, because the temperature changes will actually increase the size of the plastic fiber, because this is a plastic. The thermo-optic coefficient is very large, as we mentioned. It can expand and contract. So depending on the size tuning is also possible. And similarly, the temperature variation will also change the emitted fluorescence. This is not lasing, this is simply fluorescence coming out of the device. So in this fashion, you can have a large number of efficient sensing possible from cavities, optical cavities made of either glass or polymer like PMMA or plastic, doped with some organic dye or quantum dot to effectively monitor various physical and chemical parameters. For this particular example shown here, it is a micro sphere that is sitting here inside a chamber, which is used as a gas ammonia sensing. So this is a sphere, and through a tapered optical fiber, light is coupled into it. The output of the tapered optical fiber is given to OSA, and the transmission spectrum is continuously monitored, and the gas, the ammonia gas, is continuously monitored. Its quantity is monitored, and it is used to detect the shifting in the frequency using an OSA is used for monitoring or detecting the ammonia. And this is one important work that we have done using a microcavity because this is a graded index structure. Once light is coupled from the side, it generates whispering gallery modes inside. But since this is a graded index polymer, light is actually focusing into, while propagating, it also focuses. That means the circumference is actually changing continuously. So the area of the circumference is actually changing, means the emitted frequencies will also vary continuously. So if you take different lengths of these microcavities, you are going to expect different wavelengths that are going to be emitted. So this is a very interesting result. And lastly, most of the lasers that we talk about, they are actually emitting in all the 360 degrees. One method to get some kind of directionality or a better directionality from the microcavity lasing is to go for asymmetrical cavities. For this is a hollow structure. This is also a hollow structure. This hollow structure having a hole which is asymmetrically placed. It is not at the center that is placed. So asymmetrically it is placed. So it is more likely that more emission is going to come from this region, because in this region it is going to be more leaky. It is very less amount of confinement is going to happen. More leakage is expected from here. So asymmetric ring cavities, if you make and you monitor, if you shine some light on that, you have a pump laser, and this will act as a laser, but with some directional emission. So we have incorporated some nanomaterials, some silver nano particles, nano wires into these, so that we will be able to improve the photostability of the material, because the photostability of the fluorescent material is very important in such devices, because you are exciting such cavities with external laser. So the material has to withstand, or the fluorescent material, the organic material has to withstand the laser for a longer period of time. And our recent studies show that incorporating metal nanoparticles along with the fluorescent material in a microcavity will improve its photostability. And we are also trying to amplify this kind of radiation that are coming. So we are expecting something like this. This is the actual emission from the microcavity. We want to amplify it using an amplifier. For that, this is the original microcavity. You make use of another optical fiber which can act as a amplifier, and while passing through this amplifier, these modes are getting amplified, and they are actually shown here. So these experiments are actually being done right now. And in conclusions, the dye-doped polymer-based microcavities can be very good candidates for the fabrication of WGM lasers, and the polymer-based microcavities can offer tunable, low-threshold lasing in the visible region. Graded index, hollow, micro-ring embedded types of polymer microlasers can be used for sensing a variety of physical parameters. Photostability of organic dye-doped polymer lasers can be improved by the incorporation of metal nanoparticles. Micro-ring embedded hollow microcavity offers strong modulation leading to single mode operation. Improved directionality of the WGM lasing can be realized by asymmetric cavities. I know I was moving very fast during my last few slides. Because of the time constraints, I am stopping here. I would be happy to answer any of your doubts in this regard. Thank you very much.
Thank you. Thank you very much, sir. Dear participants, the session is open for discussion now. If you have questions, you can raise your hand and unmute yourself and ask the question to sir.
I think they have been bombarded with a lot of information in the last few days, so
Yes,
they may be
that's
overloaded.
no. That's not the problem. But you have actually highlighted the research, important aspects of research which is carried out at your laboratory, sir. That was a
Yes.
very interesting and encouraging for our participants. Thank you very much. I request one of my colleague, Mr. Akshay Mungle, to propose vote of thanks.
Thank you, sir. A presentation that have the goal of increasing others' knowledge, understanding, and abilities, then yes, it is acceptable. So first of all, good afternoon to all. I deem it is a great honor and privilege to propose the oath of thanks on the memorable session. So first and foremost, I thank our special guest, the eminent resource person, Professor M. Kailasnath, Sir, International School of Photonics, Cochin University of Science and Technology, Kerala, for his informative session. Sir, by attending your session, I can say it is very useful to our participant to increasing their knowledge and understanding about the optical sensors and its different types. Sir, you have been given the brief information about performance parameters of a sensor, optical microcavities, microresonator, optical resonator, fibroparode cavity, benefits of optical fiber, and WGM mode sensor. So thank you, respected sir. And we are extremely thankful to our HOD, coordinator of FDP, Dr. Abhijit Yadav sir, for organizing such an extraordinary and a beautiful FDP on photonics. Thank you, respected sir. I am very happy to intend my heartfelt thanks to the heads of various departments, faculty members, research scholars, and students for attending, and your corporation in making this session a resounding success. So finally, I would like to thank all the colleagues of organizing committee, Dr. Rajesh sir, Swapnil sir, Kumbar sir, More sir, and Zadke sir, and all good hearers who worked behind the screen. So finally, once again, I thank you all for your attention. Thank you, sir.
Thank you very much, sir. Very nice.
Thank you. Thank you.
Yes, sir.
Okay.
Thank you very much.
Thank you. Thank you.
Yes.